All right, so let's go ahead and finish up this last example here, and let's take a look at what happens if you're trying to find a derivative of a function that's an accumulation function, but both ends are variables, right? And so what we have to think about here is that we're measuring area. And the nice thing about area is that if you are looking at area as a whole, oops, sorry, get a smaller pen there. So if you're looking at area as a whole, that's from like some arbitrary point A to arbitrary point B, right? So we're looking for the area under the curve. If you somehow divide it anywhere, right? Like if you say, I'm going to look just from A to this point right here. Let's say it's like 3, and if I find this area and I add that area up, and then I later, go ahead and add this area up. The two sums are equal to the whole, right? And so, it's such a simple, kind of, arbitrary and kind of easy concept. And it doesn't really matter like where you select that middle point. So that's kind of what my thought is here, is that since like one end is a variable and the other end is a variable, let's just pick an arbitrary constant in the middle so that like we just break it up into two antiderivatives. So and it doesn't matter, and so you could pick whatever your favorite number is, because whatever the constant is, the derivative will be 0. So so I might rewrite this first. So I might rewrite this as saying, okay, well, my function f of x could be thought of as going from, let's say, like x minus 1 to any constant you want to pick. Like maybe pick like 0. And then, you write your function. So it's 8t plus 1 dt plus the area, or the antiderivative. And whatever you picked, you match it on the other side. So from 0 to, to the other limit, x plus 5 of 8t plus 1 dt. So you just basically break it up into two parts. So now when I do the derivative, f prime of x, so the derivative of an antiderivative will cancel each of these individual antiderivatives. So the antiderivative gets canceled, and we are substituting in x minus 1. So it's 8 times x minus 1 plus 1. But two things, right? I know, right? Remember, it's a chain rule. So the derivative of x minus 1 is just 1. So like that's not too big of a deal. But then here, the bounds are backwards. So then it's off by a negative. Oops, there it is. Plus, and then again, the derivative of the antiderivative cancel. So then this is just 8 times x plus 5 plus 1. Chain rule. Although, again, it's still just going to be a 1. But now this time I don't have to multiply by a negative, because the bounds are in the correct order. The variable's at the top. And so if we distribute, that 1, I don't really have to worry about, but the negative. So I get negative 8x plus 8, right? And then negative 1 there, minus 1, plus, and this would be 8x plus 40 plus 1 times 1 doesn't really do anything. And then this is kind of interesting. The negative 8x cancels with the positive 8x. The negative 1 cancels with the positive 1. And we're left with 48. Okay, so like if both of these happen to be like of the same variable, like just an x and an x, like something like that, like that's going to end up being a constant anyway. So that's kind of nice. So it's interesting that no matter where you pick those values, your area will be 48. And part of that reason is because no matter what x is, plus 5 minus 1 has a span of 6, right? So wherever you put x minus 1 up to x plus 5, that is going to be a span of 6. And you think about how does that function within your linear value? Well, a slope of 8, 6 times 8 is 48. So it's a good check. Doesn't always work if you're not having linear functions, but certainly, maybe makes sense intuitively. Variation rule. So split your antiderivative, right? So split antiderivative into two separate functions. Split antiderivative into two problems. And it doesn't really matter what your value is, right? Because whether you pick 0 here or 1 or 2 or 1,000 or 2020, its derivative would be 0. So it doesn't really, like I said, doesn't matter. Okay, so take a look here, warm up B. I think it's on the very next page. I thought I'd walk through these. Oh, no, actually, it's a little bit farther. It's on page 116. So on page 116, let's just look at warm up B. Let's just go, follow with me just to make sure that, this second fundamental theorem makes sense. So in this particular question, find the derivative of an antiderivative so that I know that that's going to cancel. And again, just remember that the variable that your function is as an accumulation function will be your final answer's variable. So I need to be in terms of x. So f prime of x is equal to, it's going to be something squared minus that something. And in this case, right, I'm inserting 2x squared there and there. So I kind of like that visual there. So 2x squared and a 2x squared. But then don't forget chain rule, because we're substituting a function within a function. Its derivative would be 4x. And then we simplify. So that's 4x to the 4th power, because I square that, minus 2x squared as a quantity, times 4x. So what is that? 16x to the 5th minus 8x cubed. Okay. Good, trig. Not that we have to worry about it. But it's okay that this function is a different function, not a polynomial. Again, thinking about the derivative of an antiderivative would cancel. And it will be in terms of the variable that's out here. So f prime of x is equal to cosine of something. And again, I kind of like that highlight. So kind of visualize that something goes there. That something is x cubed. And then we have to multiply by the derivative of x cubed, which is 3x squared. Now, there's going to be a point where you're going to be tempted to do like cosine's derivative, which is negative sign, but don't, okay? Because you're doing the derivative of this antiderivative, they cancel each other out. So you can't change that identity. So you still have, it's a cosine that you were originally measuring the area under. The reason we have a chain rule here is because we have more than just like a t, right? Like our t is equal to x cubed. So the derivative of t is equal to 3x squared. And think about like that dt is right there, right? The derivative of t is 3x squared. So if that helps you, kind of process that and kind of get used to this new, this thought about the second fundamental theorem. Okay, one more. And I, this one bounds are backwards. So I'm already thinking, okay, it's off by a negative. The derivative of an antiderivative cancel, so that'll go away. And it's 2 times something squared. Well, that something is 3x squared. Immediately, since every t was equal to 3x squared, then its derivative would be 6x. So there's that derivative. And then we have not a chain rule. That was the chain rule, but then we have to multiply by negative because our bounds are backwards. So that's equal to negative 12x, right? 6x times negative 2, and then that's 9x to the 4th, or negative 108 x to the 5th. Okay, so again, I just thought that going through that. That warm up, those 3 problems, again, helping to solidify this idea of the second fundamental theorem of calculus. Most of them will be kind of like in terms of like on the AP exam, most of them would be like example like 2, maybe 3. The one where you split bounds on both, it's been a while since we've seen that, but it's certainly something that could come up on the AP exam. Okay. Any questions, come on in. Otherwise, if you want to revisit the video anytime, feel free.